Over this and the next few videos, we'll tackle repeated eigenvalues, which is situations where a single eigenvalue counts more than once. Now, what does that mean? And why would a single eigenvalue count more than once? Well, you're about to find out. And there are actually two completely different ways of looking at it. There's a geometric approach and an algebraic approach. This video is concerned with the geometric approach. And if you would like to understand repeated eigenvalues from the geometric point of view, all you ever have to think of is the transformation of reflection in 3 dimensions. We have already discussed transformations with respect to a straight line in the plane. When you go up to 3 dimensions, there are really 2 kinds of reflections. Reflection with respect to a plane and reflection with respect to a straight line. And these are 2 completely different, separate examples. And we would have been just fine if we considered just one of them. But 2 is better than 1, especially in the context of repeated eigenvalues. So just to be safe, let me spell out exactly what these transformations do. And then we'll ask the question that we always ask of linear transformations. What are the eigenvalues and eigenvectors of each of these transformations? We'll start with this one. Reflection with respect to a plane is precisely what a physical mirror does. And that is why we use the term reflection in the first place, because that's what a physical mirror does. Now, to reflect with respect to a plane, you have to draw a straight line through the tip of the vector, perpendicular to the plane. We have to meet the plane, go through the plane the same distance, and wherever you stop, that's the tip of the image. And that is also why we use the term image. And not just when it comes to reflections, but for general linear transformations. Well, in any case, that's what reflection with respect to a plane does. Reflection with respect to a straight line is very similar, except now you draw a straight line through the tip of the vector perpendicular to the reflection line and through the reflection line, and you go the same distance to the other side, and wherever you stop, that's the tip of the image. So that's our transformations. What are the eigenvalues and eigenvectors of each? You should now pause the video, form your own opinion, and then come back and check with us. All right, we'll start with reflection with respect to the plane. And one of the eigenvectors is a vector perpendicular to the plane, because its image points in the opposite direction and has the same length. So this is an eigenvector corresponding to the eigenvalue of -1, because the image of V1 is -1 times the original vector. So we've got 1. What are the other 2? Well, what's another eigenvector? And you realize that another eigenvector is any vector in the reflection plane itself, because it stays unchanged under the reflection. And that's an eigenvector corresponding to the eigenvalue of 1. So let's choose any vector in the plane and say that it's an eigenvector corresponding to the eigenvalue of 1, V2. Is there another one? And there's the rub. There is another one. We can pick another vector in the plane. Why can we do that? How is this eigenvalue different from this eigenvalue? Because this eigenvalue also has infinitely many eigenvectors that could represent it, but we only choose one of them to represent the eigenspace. What's so different here? Well, what's so different here is that the eigenspace corresponding to this eigenvalue is 2-dimensional. And that is why the eigenvalue of 1 counts twice. And that is why we have to choose 2 linearly independent vectors to represent the eigenspace. This is called the multiplicity of the eigenvector. And in particular, it's the geometric multiplicity. Geometric multiplicity is the dimension of the eigenspace corresponding to the eigenvalue. Now, which vector should we choose as the second vector representing this eigenspace? Well, here we have complete arbitrariness. We can choose any vector as long as it's linearly independent from V2, V3. And we could write v2 comma v3, but just to highlight the fact that 1 counts twice, I will write 1 comma v3. And so you see that the arbitrariness is similar to this eigenvalue, because when we observe the eigenvalue of -1, we chose any vector that represents the eigenspace. In other words, spans the eigenspace. Now when it comes to this eigenvalue, we can choose any two vectors to represent that eigenspace as long as they span it. So to summarize, -1 is a single eigenvalue, and 1 is the repeated eigenvalue of geometric multiplicity 2. So this linear transformation has three eigenvalues: -1, 1, and 1. -1 is a simple eigenvalue, and 1 is the repeated eigenvalue. This completes this example. Now let's move on to this example, which is very different and at the same time very similar. What are the eigenvalues and eigenvectors of this transformation? Well, one of the eigenvectors is a vector that lies right on the reflection line. We'll call it v1. And this vector stays unchanged under the reflection. And so it's an eigenvector corresponding to the eigenvalue of 1. And in this case, 1 is the simple eigenvalue. And -1 will prove to be a repeated eigenvalue. Now where does the -1 come from? Well, the -1 in this case comes from the plane orthogonal to the line of reflection. Why? Because any vector within this plane flips under the reflection, right? Just remember what the construction is, mentally perform it, and you'll realize that this vector will flip under the reflection, and therefore is an eigenvector corresponding to the eigenvalue of -1. So we'll call this v2, and we realize that it corresponds to the eigenvalue of -1. And once again, we make the exact same observation. It's an entire eigenspace, and it is two-dimensional, because this is true of any vector in the plane. And so to be fair to the dimension of this eigenspace, we have to choose another vector from the plane, any other vector, as long as it doesn't have to be orthogonal, as long as it's linearly independent from v3, and that is the other representative of the eigenvalue of -1. And so this transformation also has three eigenvalues of -1, of 1, -1, and -1. In this case, 1 is a simple eigenvalue, and -1 is a repeated eigenvalue of geometric multiplicity 2. So this is what repeated eigenvalues are and what geometric multiplicity means. Once again, it's the dimension of the eigenspace corresponding to the eigenvalue. This completes our discussion of geometric multiplicities, and we'll next tackle algebraic multiplicity.